Hello, this is Trevor from Telecom Training. I made a series of videos about dipole, monopole, Yagi, and LPDA antennas recently. Link to those videos are in the description below. After one of my viewers saw one of those videos, I got a very interesting question from him. So I made this video because if one person asks, there must be many others wondering the same thing. The viewer started out by explaining that he does understand that when we send a high modulated frequency from a transmitter to an antenna, our signal is radiated into the ear from that antenna as an electromagnetic wave. And that is correct. This happened because the high frequency going to the antenna creates an alternating current which creates an electromagnetic field around the antenna, as shown here with both the dipole and monopole antennas. He went on to add that what he does not understand is why the coaxial cable feeding the antenna does not also radiate, since they are both copper wire with the same frequency running through them. This is an excellent question, and I'm sure that there are many others out there who may wonder the same thing. There is a very logical explanation why coaxial cables do not radiate like the antenna, even though they both carry the same current. So let's get to it. Here I have a transmitter sending a frequency of 500 megahertz to the antenna. Now I have a dipole antenna up here and it's connected with a coaxial cable. The yellow area here represents the inner conductor of the coaxial cable, and the blue area represents the braided shield, which is the outer conductor. So once we power up our transmitter, our 500 megahertz will be sent out on to the coaxial cable. It will be sent out onto the middle conductor here, and we're using 120 milliamps. Whenever we have an alternating current, which is what we have here, the frequency of 500 megahertz is an alternating current. So this alternating current will cause an electromagnetic field to be developed around this inner conductor here. And this would happen within the coaxial cable all the way up to the antenna. And this would continue to happen on the antenna. We will have an electromagnetic field develop around the antenna. And this is how antenna sends this signal out into the air. Coming back on the other element, we would have the same thing. We have our electromagnetic field here sending our signal out into the air. Now, coming back to the coaxial cable on this side, this will be the outer conductor, and we will have 120 milliamps on this side as well. But if you look closer, you'll see this side is plus 120 milliamps and this side is minus 120 milliamps. So because we have equal but opposite currents, this electromagnetic field developed around the conductors as a result of this alternating current would be cancelled, because we have equal but opposite currents, so they will cancel each other out. So once cancelled, we will have no radiation being transmitted from the cable. The only radiation transmitted would be from the antenna. It is important that the return current on the shield is the same but opposite polarity in order to cancel the electromagnetic field. If they are not equal and opposite, the cable would transmit an electromagnetic field externally like the antenna. A balun is needed when connecting a coaxial cable to a dipole so that the return current is the same. I also have a video in the description below that would explain what is a balun and why we need it when connecting a coaxial cable to a dipole antenna to prevent this problem from occurring. I hope this was helpful to you, and I would like to take this opportunity to thank my viewer again for submitting this question. This is Trevor from Telecom Training. If this video was helpful and you would like to see more videos like this one, please don't forget to like and subscribe. See you in the next video.